In the previous video, we talked about electron configuration and how electron configuration predicts bonding. In this video, we're going to focus on the idea of a covalent bond. And a covalent bond is described as two atoms sharing their electrons to form a new bond. Now, for a covalent bond, we can talk about two atoms equivalently sharing those electrons, or we can talk about two atoms where one has some greater pull on those electrons than the other, and we'll talk about what that means in a future video. There are multiple ways to describe and model bonding. Each model has its own strengths. Each model has its own weaknesses. So we should be comfortable with using multiple approaches to describing bonds. Let's use the simplified model of two hydrogens. I'm going to show a video in a second of two hydrogen atoms. We have one hydrogen, we have another hydrogen, and what's going to happen is this hydrogen with this electron and this hydrogen with this electron are going to move together. And as a result of that, we have our electrons here and here. And as they move closer together, they're going to release energy. They're going to become a more stable molecule. And so they form a new bond. We now have a hydrogen bond between, or a bond between these two hydrogen atoms. In the video, as these two things move closer together, notice how the electron cloud ultimately shrinks, it contracts when the bond is formed. And so it inherently becomes more stable because now the electron on this hydrogen is attracted to the proton on this hydrogen and vice versa. And so the whole thing becomes more stable. So here's a fairly accurate simulation of what these orbitals look like when they merge together. Notice how the animation of the electron cloud is actually smaller than the individual starting electron clouds. And that is because the product is stable. Now you might have seen an image of or a video of a hydrogen fire like the Hindenburg. Hydrogen is flammable, but hydrogen gas itself is more stable than the free elements of hydrogen apart. That is why hydrogen gas exists. Now, we're not going to talk about the energetics of this in any gory detail until about chapter 6. So let's return to how bonds form. And what we're going to use is this idea of linear combinations of atomic orbitals. We're going to use linear combinations of atomic orbitals, or LCAOs, to describe bonding in some way. Now, when we talk about orbitals, we can talk about s orbitals, and we can talk about p orbitals. Now, for an s orbital, we know that it's a sphere, and for a p orbital, we know that it is a dumbbell shape, and one of those dumbbells is shaded. But if we were to show a bonding motif between these two forms, where we have an s orbital and a p orbital, and we want to show how they are bonded together, effectively what we're going to do is we're going to add the like shaded circles. And in this case, what we end up with looks something like this, where the two empty spaces shaded add together. And if we were to look at just the electron cloud around this shape, what it would look like then would be something like this, where we add these two and fill them together. Now, we have an atom here. Atom number 1, for example. And somewhere over here, we would have atom number 2. And so the electron cloud between these atoms brings them together and causes a bond to form. We can also do the same thing with two p orbitals. And we can do this in multiple ways. We could imagine one p orbital and another p orbital. And we could add them together like this. And if we were to draw this out, effectively what we get is a shaded region above and an unshaded region below. And we're going to refer to this as a pi bond. Or we could draw these linearly. We could add these together. Let's see, let's shade them like this. So now we have something that looks like that. And in the case for bonds where the electron density is directly between two atoms, we're going to define that as a sigma bond. So we have pi bonds and sigma bonds. And for this course, that's all we're really going to rely on, are pi bonds and sigma bonds in these molecules.